Hello my friends, and welcome back to the Wow Machine channel. Wasserkraft Volcag operates as a fully integrated hydropower technology manufacturer, combining turbine engineering, electrical systems, and generator production under one roof. The technical workflow begins with multidisciplinary design, where hydraulic, mechanical, electrical, and control engineers model site-specific water conditions to determine the optimal turbine type: Francis, Pelton, Turgo, or Crossflow. Manufacturing relies on CNC machining centers, precision casting, and controlled welding processes to achieve strict tolerances on turbine runners, nozzles, and casings. Components undergo sealing, coating, and surface treatment to maximize service life in abrasive and corrosive environments. Pre-assembly inside the factory enables alignment checks, dynamic balancing, and interface verification before components reach the project site. Electrical engineering is equally integrated. WKV designs and builds its own synchronous generators, beginning with coil production, rotor winding on specialized machines, and insulation curing within an advanced impregnation system. Each generator is subjected to mechanical, thermal, and electrical testing, with load simulations and comprehensive data logging. Control systems, SCADA platforms, and protection devices are engineered in-house, allowing seamless coordination between hydraulic, mechanical, and electrical subsystems. Low, medium, and high-voltage equipment, transformers, and auxiliary systems can also be supplied and integrated into project-wide planning. This vertically unified production model reduces dependency on external suppliers, shortens delivery timelines, and ensures consistent technical standards. WKV's manufacturing site operates largely energy self-sufficient through its own hydropower plant, demonstrating the same technologies it deploys worldwide. Alpsan Aluminium operates a fully integrated aluminum manufacturing workflow built around precision extrusion, controlled anodizing, advanced CNC machining, and high-efficiency powder coating systems. These presses run with automated billet heating, precise die control, and continuous profile cooling, supporting consistent dimensional accuracy across high-volume production. The anodizing line, certified, uses tightly regulated electrolyte baths and automated sealing stages to create uniform oxide layers in multiple color ranges. Mechanical processes such as drilling, milling, or slotting can be completed beforehand thanks to 5-axis CNC machining centers, which allow all surfaces of a profile to be processed in a single clamping. This reduces tolerance deviation and ensures repeatability on complex geometries. By integrating extrusion, surface engineering, machining, and finishing under one roof, Alpsan achieves minimized lead times, reduced dependency on external suppliers, and stable process reliability across its entire aluminum profile production chain. A major technical highlight is the vertical powder coating plant, one of the earliest second-generation installations in Europe. Equipped with 20 fully automatic paint guns and a 7.5-meter profile capacity, it ensures synchronized electrostatic application, continuous curing, and a wire mark-free surface finish. Automated conveyor systems regulate profile spacing, charging, and oven throughput to maintain consistent coating thickness. Idle pressing Gauss provide fully integrated casting solutions focused on technical precision, automation, and process control for light alloy components. Their systems cover three primary casting technologies: high-pressure die casting, HPDC, gravity die casting, and low-pressure die casting, each equipped with automated cells for mold handling, metal delivery, and part extraction. This integration ensures consistent cycle times, repeatable fill patterns, and controlled solidification for optimal mechanical properties. Idle press machines feature robust tie bar structures, precision hydraulic injection systems, and user-configurable control software that regulates injection speed, pressure, and cooling rates. Standardized, high-quality components allow for stable operation and simplified maintenance. Gauss specializes in automation and robotics, integrating handling robots, degassing units, and trimming presses into gravity and low-pressure casting cells. Each system is customized to mold geometry, alloy type, and thermal management requirements, ensuring minimal porosity and dimensional variation. Both companies embed monitoring and feedback loops throughout their production lines, allowing operators to adjust process parameters in real time. Engineering teams provide calibration, testing, and setup protocols, while spare part logistics and modular designs ensure minimal downtime. Collectively, Idle Press and Gauss offer technically optimized, flexible casting platforms, capable of delivering high-precision components for automotive and industrial applications. The 2.7 LPG valve auto-assembly machine is engineered for high-precision, high-speed assembly of liquefied petroleum gas valves, combining mechanical accuracy with automation to ensure consistent product quality. The system integrates multiple synchronized stations, each dedicated to a specific assembly operation, including component feeding, insertion, alignment, torque application, and final inspection. Components are delivered via vibratory or belt feeders, and positioned using precision guides and pneumatic actuators to maintain alignment and prevent damage. Torque-controlled drivers and automated presses ensure that threaded and fitted components are joined within strict tolerances, reducing the risk of leaks or mechanical failure. Sensors at key points monitor component presence, orientation, and assembly completeness, providing real-time feedback to the central control system. Rejected parts are automatically diverted to maintain line efficiency. The machine operates under a programmable logic controller, allowing operators to configure cycle times, sequence steps, and process parameters for different valve models. Safety interlocks, emergency stops, and enclosed guarding protect operators while maintaining continuous production. Modular design allows for quick changeovers between valve sizes and types, minimizing downtime and maximizing throughput. Integrated quality control stations, including torque verification and leak testing modules, ensure that each assembled valve meets stringent industry standards. The machine's precise handling, automated control, and modular flexibility make it suitable for medium to high-volume LPG valve production, while maintaining consistent technical performance and safety compliance. The machining of high-end electronics housings using Datron high-speed milling machines demonstrates the combination of precision engineering, process optimization, and advanced automation necessary for modern manufacturing. The project focuses on producing complex geometries in aluminum and other non-ferrous metals while achieving high surface quality within minimal cycle times. The Datron M8 Cube is employed for this purpose, utilizing specifically tailored milling strategies and cutting tools to reduce machining time and tool wear. For instance, tool No. 2, 26 mm long, is used along its full cutting length with a Z infeed for rough milling operations. Subsequently, dynamic pocketing with a 1 mm transverse feed ensures efficient material removal, smooth surface finish, and minimal mechanical stress on the cutting tool. This method is faster and more precise than conventional milling strategies, which often require multiple passes and result in higher tool wear. Traditional vertical machining centers are generally designed for large, heavy components and often use oversized cutting tools that are not ideal for smaller or more intricate parts. They also require highly trained operators, making staffing costly and workflow less flexible. The M8 Cube, in contrast, is specifically engineered for complex part machining. Its rigid, low-vibration design ensures high stability and excellent surface quality. A high-speed spindle capable of 60,000 revolutions per minute, paired with feed rates up to 22 meters per minute, allows high material removal rates without sacrificing accuracy. The machine's automated tool changer, with up to 143 stations, reduces setup time and allows multiple tools to be available in a single run, minimizing downtime between operations. The M8 Cube features a large 40 inches by 33 inches work area within a compact 69 inches by 69 inches footprint, making it suitable for both large and nested smaller parts. The polymeric concrete table provides structural rigidity and vibration dampening, while cutout options allow vertical mounting for taller components. Operators can easily configure multiple setups on the bed, enabling rapid reaction to urgent production changes without interrupting ongoing jobs. The system is controlled via the Datron Next software on a 23 inches touchscreen, allowing intuitive visual programming, job monitoring, and real-time adjustments. Precision is further enhanced through the careful coordination of toolpaths and automated machining sequences, ensuring repeatable accuracy for every part. Secondary operations, often required with traditional milling centers, are minimized or eliminated, which increases overall workflow efficiency. The M8 Cube's capabilities also allow manufacturers to explore new markets by producing intricate, high-tolerance components that were previously impractical or impossible to machine in-house. With power ranging from 0.6 to 4 kW, the M8 Cube balances energy efficiency with machining performance. In summary, the Datron M8 Cube provides a technically optimized solution for the high-speed, high-precision machining of electronics housings and other complex parts. Its advanced milling strategies, rigid construction, high-speed spindles, and intelligent automation create a workflow that significantly reduces cycle times, enhances surface quality, and maintains consistent precision. The machine's compact footprint, large work area, and modular setup capabilities allow manufacturers to increase production agility, improve efficiency, and expand the range of components they can produce, all while minimizing tool wear and operational complexity. This combination of features positions the M8 Cube as a highly effective tool for modern manufacturing environments requiring both speed and technical precision. At Alcoa's aluminum rolling mill, the process begins once an ingot is cast. Each ingot is first scalped, shaving the top and bottom to remove surface impurities and achieve a smooth, mirror-like finish. Preheating follows, making the aluminum pliable for rolling while establishing its metallurgical properties. This is done in one of the facility's pusher furnaces or a box furnace. The hot rolling stage begins at the reversing mill, where two 7,000-horsepower motors drive the rollers to reduce a 40,000-pound ingot from 21 inches to 1.5 inches thick, simultaneously elongating it from 30 feet to 400 feet. After the flying shear removes the head and tail, the continuous mill flattens the slab further to 1/8 inch, producing a coil about a mile long. Cold rolling follows after the metal cools to 200 to 300 degrees Fahrenheit. At speeds approaching 60 miles per hour, the cold mills reduce the aluminum to its final thickness, just thousandths of an inch. The process transforms a massive ingot into a thin coil that could stretch up to 10 miles. The aluminum then proceeds to the finishing department for final preparation before shipment to customers. The APV 1.25M4 punching and drawing machine is designed for the production of pressed mesh, commonly called perforated mesh, from cold-rolled sheet steel up to 1,250 millimeters wide. It weighs 2,300 kilograms. Powered by a 5.5 kW electric motor at 380 V, it features a set of 40 x 89 knives, a mesh cutter, a length counter, a roll winder, and auxiliary support tables for both the sheet and mesh. In the video, a 2,500 x 1,250 mm sheet of 2 mm thick cold-rolled steel is processed in 22 minutes, producing 35 meters of mesh covering 44 square meters with a 1.5 mm bridge thickness. The machine is equipped with a movable control panel, stroke counter, forced mesh winding mechanism, and a mesh cutting system. Key power elements have double safety margins with adjustable settings, ensuring high reliability and consistent output of approximately 2 square meters per minute. All components are built with a 5-fold safety margin, using tapered bearings that can be adjusted to eliminate play, an important factor in punching drawing machines. Standard bearings and belts ensure easy maintenance. Around the forge, white-hot steel is shaped under the immense impact of an open-die hammer system, demonstrating a core process of modern industrial blacksmithing. The workflow begins by heating the billet to forging temperature, where the metal reaches a plastic state suitable for deformation without fracturing. Once transferred to the hammer bed, the billet is positioned between the upper and lower dies, which remain flat or minimally contoured to allow free movement of material during each strike. With every blow, the hammer delivers controlled tons of force that elongate, spread, or reduce the billet according to the forging plan. Operators continuously rotate and reposition the workpiece to maintain uniform grain flow and prevent internal stress concentrations. The repeated high-energy impacts refine the steel's microstructure, increasing toughness and directional strength. For large cross-sections, the process may include multiple heats and progressive reductions to reach the required dimensions. The result is a precisely forged component with improved mechanical properties and structural reliability. The connecting rod in this video is produced using a 31.5 kilojoules CNC hydraulic die forging hammer, a precision machine widely used in modern forging industries. CNC forging hammers are applied across a range of sectors, including automotive, motorcycles, hardware, hand tools, stainless steel tableware, and aeronautics, with a particular focus on precision forging. The forging process begins with a preheated billet, usually made of low-carbon steel to ensure optimal ductility and minimal material defects. The CNC hydraulic hammer delivers controlled, high-energy impacts to shape the billet into the rough form of the connecting rod. Its advanced CNC system allows precise control over stroke, force, and hammer speed, ensuring consistent dimensional accuracy and metallurgical quality. Following the initial forging, the connecting rod undergoes trimming, piercing, and finishing operations. Excess material, known as flash, is removed to achieve the exact geometry, while holes and cutouts are formed according to design specifications. The CNC hammer's repeatable accuracy reduces tool wear, minimizes material waste, and allows for faster production compared to conventional forging methods. This process emphasizes efficiency, low operating costs, and high-quality output. By combining high-speed, high-force impact with precise computer control, the CNC hydraulic die forging hammer produces connecting rods with superior mechanical properties, tight tolerances, and consistent microstructure. The result is a forged component capable of withstanding extreme stresses in automotive engines and other high-performance applications. The CNC forging hammer is therefore integral to modern forging, providing both high production efficiency and precision in complex components like connecting rods. T&T Tubecraft utilizes advanced CNC tube bending and manipulation technology. Their all-electric machines deliver superior accuracy and high repeatability, ensuring consistently precise bends for complex tube components. This modern approach allows for efficient production of intricate geometries, while maintaining strict quality standards across every part. Datron Corporation is a specialized manufacturer of wire ropes, offering comprehensive technical solutions for production, testing, and customization. The company's manufacturing process integrates advanced machinery and precise manual operations to ensure high-quality rope products suitable for industrial and construction applications. Production begins with the use of an automatic measuring machine, which accurately cuts wire strands to the required lengths. A triangular vise ensures secure handling of the wires during assembly, while the 3000 topless machine, supplied by Telluride, twists the strands with high precision and consistent tension. This ensures the structural integrity and uniformity of each rope. For quality assurance, Datron employs a vertical tensile testing machine by Omsler, capable of measuring the breaking strength and elasticity of the ropes under controlled conditions. A wire cutting machine, also from Telluride, is used for precise separation and trimming of components during production. Specialized rigging ropes are produced using both hand braiding techniques and turntables, allowing for custom configurations and reinforced loops. Every step, from automated cutting and twisting to manual braiding and assembly, is designed to ensure durability, strength, and safety. Datron Corporation combines high-end machinery with skilled craftsmanship to deliver wire rope products that meet the rigorous demands of modern industrial applications. Siemens' turnkey structural steel fabrication system operates as an integrated production environment engineered to maximize accuracy, throughput, and repeatability across all stages of steel processing. The workflow begins with digital modeling, where project geometries are transferred from BIM platforms into a centralized production control system. One of Siemens' standout technologies is the SynBeam machine, a fully automated system for creating a corrugated web with optimal energy under very high loads. The technology starts with a rolling of the steel coil, then cutting, adjusting the length, and welding the web to the wing's surface using robots. The machine also has the ability to cut plasma to create errors or customize the shape during the framing process. In addition, Continuous laser scanning ensures the accuracy of the wood geometry. Material handling forms the backbone of the process. Steel profiles are automatically loaded, aligned, and conveyed through preparation lines equipped with shot blasting machines and coating stations. These units remove surface contaminants, create a uniform profile finish, and establish the required adhesion conditions for primer application. The cleaned beams then move into high-precision cutting and drilling cells. CNC-controlled thermal cutters, bandsaws, and multi-axis drilling units execute programmed operations with tight tolerances, ensuring consistent fit-up during assembly. A defining feature of Siemens' system is the robotic welding technology integrated directly into the assembly workflow. Using vision systems and adaptive tracking, robotic arms position themselves along the steel members and execute continuous welds, maintaining uniform penetration depth and bead geometry. This automation reduces warping, minimizes manual rework, and maintains weld integrity even on long or repetitive seams. For complex nodes and intersecting members, fixtures hold components in precise alignment, while sensors verify dimensional compliance before welding begins. Subassemblies progress through fit-up zones, where plates, stiffeners, gussets, and brackets are accurately positioned using laser projection systems. Once components are tack welded and verified, robotic or semi-automatic welding systems finalize the joints using MIG/MAG or flux cord processes suited to the steel grade and expected load conditions. Quality control is embedded throughout the production sequence. Ultrasonic, magnetic particle, and visual inspections verify the structural integrity of welds. Dimensional checks ensure compliance with fabrication tolerances, especially in areas where steel connections interface with concrete or mechanical systems on the construction site. All inspection data is logged into the digital model, creating a complete traceability record for each member produced. After welding and inspection, finished steel components enter the finishing line for surface treatment. Primer coatings or specialized corrosion-resistant layers are applied in controlled booths to achieve consistent film thickness across beams, columns, and plate assemblies. Each element is then transferred to a curing area, where temperature and humidity are regulated to meet coating specifications. Final logistics are coordinated through automated storage racks and tagged inventory management. Members are grouped according to erection sequence, allowing construction crews to assemble the structure efficiently once materials arrive on site. The combination of machine precision, automated welding, digital traceability, and coordinated handling produces structural steel elements that interface cleanly during erection, reducing on-site adjustments and maintaining project timelines. The model DTS-03 Suffolk dual-tooth setter is engineered as a compact industrial-grade system designed for fast, precise bandsaw blade tooth setting. Its defining feature is the ability to set two teeth simultaneously, one on each side, using paired upsetting and downsetting tool bits. The blade is secured with a clamping mechanism that applies approximately 500 pounds of force, stabilizing the body of the blade to prevent distortion during adjustment. A gauge block ensures each tooth is positioned at the correct height, typically 0.160, above the clamp plates, optimizing feed rates and reducing gullet strain. Once clamped, the upsetting tool bits apply roughly 350 pounds of pressure to form the required set, while the downsetting tool bits act as mechanical stops to remove excess set and maintain uniformity. Independent adjustment of each bit pair allows tooth accuracy within plus or minus 0.002 per side. The advanced lever indexes teeth into position and accommodates blade pitches from 1/2 to 1:1/4, with tooling modules adjustable for larger pitches. A clamp-on set gauge supports periodic verification. After initial setup, a 14 FT blade can be set in only a few minutes, delivering consistent, repeatable results.